Hello and welcome to my classical physics channel. Here we have a friction related problem. We'll try to solve it for acceleration of the larger block. So we have two blocks, one larger block with mass m, smaller block with mass small m. There's a string which goes through these three pulleys, and the smaller block is left hanging. So we are required to find the acceleration a capital M of the larger block towards the right hand side, given the coefficients of friction mu1 and mu2. Let's begin. So we first of all construct the free body diagram of the smaller block. If you look at the smaller block, we have the weight mg which acts downwards on the smaller block, the tension T which acts on the smaller block through the string here. Then as the smaller block tries to slide down the larger block, the force of friction tries to oppose any related motion to happen, and hence it acts upwards on the smaller block, which we denote by F1. And there is lastly normal reaction which acts between the two blocks. Let's call it N1. Between this larger and the smaller block, let's call it N1. What follows is that the force of friction between any two bodies is equal to the coefficient of friction between the two bodies multiplied by the normal reaction that the two bodies have. So here the normal reaction is N1, the coefficient of friction is F mu2. So the force of friction which acts between the two bodies F1 here is equal to mu2 times N1. So this completes the free body diagram of the smaller block. Now going to the larger block. The larger block here has got mass capital M, so the force of gravity acts downwards, capital Mg. The force of friction which acted F1 on the smaller block in the upward direction by Newton's third law acts downwards in the larger block, so we denote it by F1 here. There is a normal reaction which happens between the ground and the block, which we denote by N2. There is a force of friction which acts on the larger block in the backward direction as it starts to move rightwards, which we denote by F2. Now F2 will always be equal to this N2 multiplied by the coefficient of friction between the ground and the block, which is mu1. So F2 is equal to mu1 times N2. This completes the friction problem for the larger block. But in addition to these forces, we must understand that the pulley through which the string passes is also a part of the larger block. So any forces which this pulley experiences should be added in the free body diagram for the larger block. If you look at the pulley here, as the tension goes through the string passing through this pulley here, the tension tries to pull this pulley rightwards and downwards. So there are two additional components of tension which this free body diagram needs to incorporate through the pulley. So we have one tension acting rightwards here and one acting downwards here. So this completes the free body diagram for the larger block. Now we have two free body diagrams, and in both of them we have two axes on which the forces are accounted for, the x-axis and the y-axis. So we can come up with 2 plus 2, 4 equations through usage of this free body diagram. But we will still be falling short for one equation to solve for our variables. So where do we get that equation from? We get that equation by making use of the constant here. You can see that the length of the string in this problem remains constant no matter what the accelerations of the two bodies are. The length of the string always remains constant. So if at an instant of time we decide to call the distance between the larger block and the wall as x, and the distance between this pulley on top and the smaller block as y, we can say that this x, this length, plus this length, which is always a constant as it is between two fixed pulleys, so x plus c1, this length, plus x again, because this length on top is equal to whatever the distance is here, so that is going to be x again. So here we incorporate x plus the length of the smaller block from top, which is y. When we add these four components, we get the total length of the string. So x plus c1 plus x again plus y is equal to L equal to constant. Now if we differentiate this equation with time, and then double differentiate again with time, we get 2 times d2x by dt square is equal to d2y by dt square. We take a modulus here because we are interested only in magnitudes and not in sign. So what it essentially says is that 2 times a capital M is equal to a small m, or in other words 2 times the acceleration faced by the larger block rightwards is equal to the acceleration faced by the smaller block downwards. So the larger block has one component of acceleration, which is a capital M rightwards. The smaller block has an acceleration downwards a small m, which is given by this relationship. The smaller block also has a component of acceleration towards the positive x-axis as it is attached to the larger block. So it will also experience a x-axis component of acceleration given by a capital M. So with these equations, these two free body diagrams in this relationship, we can have to solve for a capital M, that is the acceleration experienced by the larger block in the right hand direction. We need to apply the free body diagrams here. So talking about the small free body diagram, small bodies free body diagram, here we can see the only force which is acting in the x-axis here is N1, that is the net force. N1 is equal to mass times acceleration in the x-axis, which is a capital M. Remember, we just said there is a x-axis component of acceleration for the smaller block, which is equal to the acceleration of the larger block, which is a capital M. So this is the first equation we get. Then there is another equation we will get from the y-axis, which is mg minus t minus f1. Mg minus t minus f1 is equal to m times acceleration in the y-axis, which is a small m. So these are the two equations we get from the small bodies free body diagram. Likewise, if we look at the large bodies free body diagram, we'll get two more equations, one from this axis, y-axis, and one from the x-axis. So if you look here, we have two more equations here. So we have 1, 2, 3, 4 equations in addition to the relationship we derived between the two accelerations. If we make use of these four equations, I would quickly tell the third and the fourth equation. The third equation says tension downwards plus weight downwards mg plus f1, tension plus weight plus f1 is mu 2 n1 is equal to n2, as there is no acceleration in the y-axis for the larger body, so the force is balanced. Likewise, in the x-axis we have 2 times tension minus f2, which is mu 1 n2. 2 times tension minus mu 1 n2 minus n1 is equal to m times am. So this is the last equation we have. Solving for these four equations and making use of the relationship we derived earlier, we can solve for a capital M. And here is the expression given for a capital M. I would like the students to solve for the expression, as this channel is more about concepts rather than equation solving. So we will try to come up with this expression for a capital M using these equations. I have solved the same here on another page, but I would really want the student to go through these equations and try to come up with the solution on their own. To match the solution, I would like to get them a closer look here. So all the best in trying to understand these concepts and solving for this equation. Till then, for the next problem, goodbye and good luck. Thank you.